The 300-mile corridor connecting Tokyo to Osaka is Earth's densest industrial zone. Millions of components, engineers, and data packets flow across this spine every day. When the Shinkansen began operations in 1964, it dropped a high-speed transit node directly into an undeveloped patch of Kanagawa Prefecture, Shin Yokohama. That single infrastructure injection triggered a chain reaction, turning a transit waypoint into an urban research node. For hardware developers, proximity is survival. This station provides a direct zero-transfer line to the heavy manufacturing floors of Nagoya and Osaka, allowing engineers to physically interface with their supply chains in under 2 hours. Comparing operating expenses reveals a structural advantage. Shin Yokohama rent is exactly 60% of the Tokyo baseline. Combine this with localized talent data. Yokohama houses over 140,000 engineers, forming a dense labor pool directly overlapping the transit hub. Access to lower rent, high-speed rail, and thousands of engineers completely alters the capital equation. Geographic arbitrage provides the liquid capital required to finance the development of next-generation hardware. Developing deep tech hardware is notoriously expensive. Small and medium-sized enterprises, SMEs, face a continuous burn rate, requiring massive capital investment just to prototype their designs. The operating expense saved through Shin Yokohama's geographic arbitrage is immediately reallocated into hard tech R&D. Companies fund new clean rooms, purchase specialized testing equipment, and retain elite technical talent. The result of that localized spending is a complete industrial internet technology stack, compressed entirely into a single transit district. While many tech hubs are dominated by a single monolithic corporation, this landscape is populated by independent, highly specialized SMEs. To understand how this decentralized engine functions, we will deconstruct this cluster by building its technology stack from the ground up, layer by layer. Geographic arbitrage lets these companies physically build the entire hardware stack within a single square mile. A decentralized tech cluster immediately faces a structural problem. Highly specialized, isolated hardware vendors need a way to access and integrate complex global intellectual property without maintaining massive international procurement teams. The solution is a routing layer. In Shin Yokohama, that layer is anchored by Mechnica, a technology trading company that commands a 22% domestic market share in semiconductors. Mechnica relies on field application engineers. The Mechnica building acts as a central hub, receiving raw global IP packets. These engineers translate and customize the complex specifications, then rapidly distribute this localized IP outward, feeding it directly into surrounding Japanese manufacturers and system integrators. This continuous outward flow of advanced components creates a gravity well. It pulls testing facilities, certification services, and specialized board design firms directly into the surrounding office buildings to support the integration process. Field application engineers operate as the high-bandwidth routers of the ecosystem. They take a fragmented collection of independent vendors and synchronize them into a highly functional supply chain. With the routing layer established, we move down to the foundational physical layer of the stack, non-volatile memory, spearheaded by a specialized firm called Ramseed. Ramseed specializes in ferroelectric memory, or FerRAM. Here is its crystal lattice structure. While traditional memory traps electrons, FerRAM uses physical movement. Apply an electrical field, and zirconium and titanium positive ions physically shift across the lattice barrier. Because these ions lock into their physical positions, the memory is non-volatile. Even if the system loses power entirely, the data remains intact. Despite retaining data without power, this physical ion shift occurs so rapidly that it allows for write speeds comparable to extremely fast SRAM. This logarithmic chart compares rewrite endurance. Standard EEPROM degrades after roughly 1 million cycles. FerRAM pushes that threshold to an astonishing 100 trillion rewrite cycles before physical degradation occurs. Alongside FerRAM, Ramseed develops parallel resistive RAM, or ReRAM, engineered for extreme low power draw. It consumes a mere 0.15 milliamps at 5 MHz. These specifications are mandatory requirements for continuous, battery-less data logging in devices like smart meters and industrial robotics, where replacing a power source is either impossible or cost-prohibitive. The entire cluster's ability to process data at the edge relies heavily on the quantum-level manipulation of crystal structures to solve physical data retention bottlenecks. High-end memory is useless if the physical connection to the motherboard fractures under stress. This brings us to the mechatronic layer. Automotive and industrial environments are hostile. High-frequency vibrations constantly threaten the physical integrity of every soldered joint and silicon component. To prevent mechanical failure, Iriso Electronics developed the floating connector. Here we see its 3D cross-section bridging two circuit boards. As the bottom board vibrates, the flexible internal joint absorbs the kinetic energy. It flexes independently, keeping the top connection perfectly stable. This exact mechatronic tolerance is specifically required for advanced driver assistance systems, where a dropped signal from a fractured pin could result in a high-speed collision. You can see this hardware alignment across the district. NIFCO, a company traditionally known for industrial fasteners, placed its global R&D office right here to manage their transition into integrated smart components. Software reliability in the physical world is entirely dependent on rigid mechatronic stress mitigation. Moving upward in the architectural stack, we reach the data processing stage. Hardware generates raw physical signals, but a dedicated software layer must compile that data into usable value. AcroQuest technology operates as the intelligence layer for the cluster, taking responsibility for making sense of the hardware output. Their EndoSnipe platform ingests massive arrays of sensor data. Raw data flows from the physical layers below, moving upward into a structured interface. The logic automatically filters the stream, flagging anomalous spikes in red before they hit failure thresholds, optimizing energy consumption. Shin Yokohama's software layer is also built for immense scale. Neo Japan, a highly prominent firm in the district, developed a groupware platform called DeskNet's Neo, which currently supports a user base of over 5.3 million people. Neo Japan illustrates the extreme organizational efficiency possible here. They generate massive recurring revenue streams while maintaining a tight, streamlined workforce of roughly 300 employees. The top of the stack acts as a translation engine. It turns raw physical signals into actionable, scalable enterprise logic. Zooming out, we view the completed vertical architecture. The stack routes from Macnica to Ramseed's memory, up through Iriso's connectors, and into AcroQuest's software. Because this stack is so tightly integrated, massive international tech giants embed themselves here to access this localized intellectual property. The British semiconductor design firm ARM maintains a presence in the district with a highly specific mandate, deploying specialist teams to design automotive GPUs for next-generation mobility platforms. Sensata Technologies established a global business center here for similar reasons. They use Shin Yokohama as the geographic nexus for automotive sensor integration across the entire Japanese manufacturing sector. Global tech giants embed core research and development teams here to physically interlock with the SME stack. The ultimate output of this ecosystem's convergence is the software-defined vehicle, or SDV. An SDV represents a structural shift in automotive engineering. Vehicles are evolving from primarily mechanical machines into rolling server racks, where software dictates the vehicle's entire functionality. These vehicles cannot function in the real world without the exact layers we just explored. They require vibration-proof mechatronics, extreme endurance edge memory, and flawless real-time processing pipelines. Institutional frameworks like Tech Hub Yokohama and iTop Yokohama are actively accelerating this process. They act as matchmakers, pulling these highly specialized layers into global pilot programs and real-world testing. Future technological dominance will not belong solely to abstract software monopolies. It will belong to dense physical ecosystems that have mastered the unabstractable mechanics of the real world.